Hi, I'm Manish Maheshwari. I'm a Principal Solutions Engineer at Cloudera. Today I'm happy to talk to you about how to scale Impala and some of the common mistakes and best practices for scaling Impala. A quick overview of the agenda. We'll talk about Impala. We'll talk about some KRPC improvements that Impala has now. We'll talk about some scaling issues and solutions for them, understanding how to read and understand query profiles, and some key takeaways. What is Impala? Impala is an open source MPP database engine. It runs on a C++ backend and has support for runtime code generation, streaming aggregations. It supports multiple storage engines like HDFS, S3, ADLS, Kudu. We are adding support for Google Cloud Storage and multiple formats like Parquet, text, sequence, ORC, etc. It has support for authentication, authorization, row and column access control, and is run by over 1400 customers and 97,000 machines that are Cloudera customers. It is now scalable even more, with running on clusters greater than 400 nodes. Let's take a high-level look at the Impala architecture. The architecture can be broken into three layers: the metadata layer on the top, the execution layer in the middle, and the storage layer down below. The storage layer can be HDFS, Kudu, ADLS, S3, Azure, etc. The Impala daemons form the middle execution layer. Each of the Impala daemons is broken into three parts: the query compiler, the query coordination, and the query execution. On the top, at the metadata layer, we have the state store that distributes cluster state, cluster health, running queries, and the metadata among all the Impala daemons. The catalog daemon has the job of retrieving the metadata from the name node, the Hive meta store, and policies from Ranger, and it creates something called as metadata cache. This metadata cache is distributed using state store to all the executors. How does a simple select query in Impala run? What we see over here is when a request arises via JDBC or ODBC to a particular Impala daemon, that Impala daemon becomes the query compiler and the coordinator for that query. It will compile the query, it will pass the plan, it will create the plan, it will build the runtime plan and distribute it to all the Impala executors. It will then coordinate the execution of that query. The executors themselves would read the data from the storage, do the filtering that's required, execute the joins or aggregations that are required, and finally send the data to the coordinator for the final sort or the final group by. The coordinator then returns the data to the calling application. Now, what is KRPC? KRPC is the acronym for something called as Kudu RPC. It was called Kudu RPC because this protocol for inter-daemon communication was built first for Kudu and then used for Impala. It reduces the overall connections in the cluster. It reduces the stress on MIT-KDC and supports both synchronous and asynchronous RPCs. KRPC supports connection multiplexing, which is important because in the past, for each query, Impala daemons used to create a new connection to other Impala daemons, and that used to cause a lot of connections on the cluster. By implementing KRPC, on an average, we have seen performance improvements of 2x or 3x on the conservative side. On the aggressive side, we have seen improvements as good as 5x to 10x. Some stats for KRPC. We have seen that after implementing KRPC, the number of queries per hour went up significantly than with Thrift RPC. We are also able to run concurrent queries, higher number of concurrent queries with successful completion. So what you see on the right, you see 64 concurrent queries. With Thrift RPC, we could run only 73. With KRPC, we could run 100. The overall runtime also decreased. So what you see over here is 64 concurrent threads. Number of queries per hour with Thrift were only 87, but with KRPC now you could run 571. So KRPC that was introduced in CDH 515 has improved Impala performance overall. Let's talk about some scaling issues. We have customers running Impala successfully, and now they have more use cases to onboard. The amount of data increases, the amount of metadata increases, the number of tables and partitions increase, number of concurrent queries increases. when you add more nodes to a cluster, they typically see that their performance goes slower. How do you fix that? The first thing to do is understand how the metadata cache works. The Impala catalog and the daemons cache the Hive metastore metadata, so table information, partition information, and the HDFS block location that includes the path of each block and the name of the file. The amount of memory required to cache this data is significant. The calculation goes like number of tables into 5 KB, number of partitions into 2 KB, number of files into 750 bytes, plus each block into 300 bytes, plus any statistics for that table. That's a significantly large amount of memory that's required. So we had a large telco that had around 56,000 tables, and their catalog metadata was around 80 GB. At this, their GC time went up significantly. They had reduced memory for query execution. They had out of memory issues on the catalog daemon. They had long time to load metadata, and they had slow performance for even DDL and DML statements like describe table or show table. To understand why this is so, we look at this diagram that explains that the catalog D via the state store distributes the metadata to each of the daemons. Now, the key here to understand is not each daemon requires a metadata. The metadata is required only for those daemons that are coordinating the query and compiling the query. It is not required for the executor daemons. So we decided to change this, but some intermediate steps before we decide to change it. We recommend customers to merge small files, refresh tables, refresh partitions, avoid ingestion processes that cause a lot of small files, use larger block sizes on HDFS, use optimal partitioning strategies, don't under partition your data, don't over partition your data, and few other storage technologies like HBase or Kudu, but they didn't help significantly. So we introduced the technology of dedicated coordinators. With dedicated coordinators, we broke down the Impala daemons into two sets of roles. The first set of role was the query coordinator. Its job is to compile the query, create the execution plan, and it needs the metadata to be able to do that. The executors get the execution plan from the coordinators, and all they have to do is run the query and get the results back to the coordinator, and they don't need the table metadata. This reduces the amount of memory required for storing metadata, for distributing metadata, and improves overall cluster stability. Benefits: executors need less memory, state store does not need to send the metadata to all the daemons, faster metadata updates, faster state propagation. Coordinators don't need to be on the data nodes, they can run on separate edge nodes of the cluster. So with dedicated coordinators, the updated architecture looks like this, where you see over here that the catalog daemon distributes the metadata only to the query coordinators. The executors do not have the metadata any longer. This has improved the performance of Impala significantly, reducing the amount of memory required on the executors and making sure that the executors run faster, just doing their job, which is running the queries. Some best practices for setting dedicated coordinators. Thumb rule: start with just one coordinator for 50 to 60 executors. Write on an edge node. They require some disk for to write any operator data that is spilling to disk onto the disk so that it can be retrieved by the calling application. Add another coordinator when CPU utilization goes up to goes beyond 70 to 80%. Use the load balancer in front of the coordinator and make sure that the first coordinator is active, the second coordinator is a fallback passive coordinator. Use sticky connections on the load balancer. Increase the front-end service threads so that all the clients that are trying to retrieve the data can connect to just a single coordinator or two coordinators. Increase the Java heap on the coordinator so that they can keep the catalog without requiring that much heap on the other nodes. Increase the metadata loading threads if you wish to, if you have a significantly large catalog. So this improvements got us to a very healthier Impala state, but we decided that it needs to improve even further. What you see over here is now we have something called as metadata on demand. By metadata on demand, what it does is, let's say if coordinator 1 requires the metadata of table A, coordinator 2 requires the metadata of table B, and coordinator C requires the metadata of table C, With the newest version of Impala, the metadata is given to only the coordinators when they ask for it, rather than sharing or distributing the metadata all the time. In this case, the metadata for the required tables is sent on demand to the required coordinators. This way, the coordinators can manage their memory even better. The memory for the catalog is managed as a LRU cache. In such a setup, they can invalidate old tables, they can remove the metadata of those tables that are no longer required when the coordinator is running under memory pressure, or simply on the basis of time when the metadata becomes stale. In such a scenario, you also get a smart invalidation cache, where when any time if a table is recreated or table is dropped, the cache is invalidated so that the other nodes are aware of what has happened. The way that all of this works, it works via something called as high metastore notifications. What we do is the coordinators, when they do any metadata operations, they generate HMS notifications, and these HMS notifications are distributed throughout the cluster. By processing these notifications, the coordinators are made aware of what changes have happened in the cluster. For example, table has been created, table has been dropped, partition has been added, partition has been dropped. Beyond Impala, we use the same HS notifications even in Hive and Spark. Thereby, when somebody creates a table in Hive or loads data into a table in Spark, those metadata notifications make Impala aware of those changes. To enable metadata on demand, we ask customers to set the catalog topic mode equal to minimal and use a local catalog equal to true. This is already by default on in Impala 4.0. In the earlier versions, you have to actually turn it on. There's time-based catalog eviction, so you can set in how much time do you want to invalidate or you want to forget tables that are no longer accessed. There's also a memory-based eviction, where you can say that at the time of Impala metadata memory, when it comes to 60% of the configured heap size, you can ask Impala to start purging out the old tables that are not accessed recently from the memory. This has significantly improved Impala performance by making sure that the coordinators only have required metadata with them, rather than having all of the metadata to all of the coordinators all the time. With this, the refreshed architecture of Impala looks like below. You have the same storage layer. Your execution layer is now broken up into query coordinators and query executors. Your state store and catalog remain the same, but the amount of work that they do has significantly reduced. The state store still distributes the state, distributes the health of the cluster, distributes the information of how many queries are running at all the given time. The catalog only sends a required metadata to the required coordinator when the coordinator asks for it. Let's talk about few more topics with Impala. Let's talk about admission control woes. By default, admission control should be enabled for every cluster, and default memory should be set for each pool. Okay. This is a problem where we have seen many customers not setting it, either not enabling it or not setting default memory. You have to understand that this should always be enabled. Impala, like every other database engine, use heuristics and statistics to determine how much memory is required per node for a particular query to run. However, at times these numbers could be off, and some time stats are not available. In such case, Impala tries to be conservative of how much memory is required, and in many cases it overestimates the amount of memory. Because memory is overestimated, you have thereby running queries with more than required memory, and thus the overall number of queries on your cluster goes down. This is a situation called as under admission, where you could actually run more queries on the cluster, but because of missing stats or because of Impala overestimating the stats, you are running less number of queries than what you could run on the cluster. You would see queries OMing out due to memory, and errors could be that queries are not admitted, or they time out in the queue, waiting in the queue, because there was not enough free memory on the cluster. So remember to always enable admission control, to always set the default memory limit, and in new version of Impala you can set the min and the max memory limit and ask Impala to automatically try to adjust a memory for a particular query between the min and the max. Thereby Impala will look at the min, which could be 500 MB or 1 GB per node, the max, which could be, let's say, around 4 gigs to 6 gigs is the max that we have seen per node, and then Impala will try to guesstimate a range between them on the basis of stats and heuristics. On the command line you can set mem limit per query or per pool depending on how you set it, and thereby you are able to run more number of concurrent queries in your overall Impala cluster without having to run out of memory. What would happen if a query actually required a lot of memory? What would happen is, in today's world, all Impala operators can spill to disk, which means that if a query really required, let's say, 10 gigs of memory per node and it only had 4 gigs of memory, it will start writing it to a disk and then wait for the next step to start, and then it will stream back the data by reading it off the disk. Some information about admission control. Admission control runs decentralized, which means if you look at any Impala query plan, you would see that the queries are typically admitted or rejected or queued in a matter of nanoseconds. When you take decisions in a matter of nanoseconds, you have to make a decision then and there on the basis of the state information available with that coordinator. You don't have the luxury to talk to all other coordinators, because that cannot take nanoseconds to finish. Thus, each coordinator makes an independent decision whether to admit or not to admit a query. That is where admission control for Impala is very fast. However, during times when load is very heavy, it could be a little bit imprecise. This is where you have a chance of over-admitting the queries, especially when you have a lot of Impala coordinators. This is where we recommend customers not have more than 2, 3 or 4 Impala coordinators in their cluster, depending on the cluster size. For clusters more than 100 nodes, maybe 2. For clusters more than, say, 300 nodes, maybe 4. But beyond that, we don't recommend any more coordinators. The more coordinators you have, the more chances you would have of over-admitting queries. We also recommend customers to let queries queue up a bit. The total number of concurrent queries that we recommend for Impala is somewhere in line with the number of threads that you have on your data nodes or your Impala executors. So let's assume on Impala you have, for your cluster, you have 32 core nodes. 32 cores equal to 64 threads. You can set the number of concurrent queries running on the entire Impala cluster somewhere close to 64. You can go a little bit higher depending on how IO heavy your queries are, or a little bit lower depending on how compute heavy your queries are. But that's a safe range, and we would recommend other queries to queue up and wait in the pool or wait in the queue until they're admitted. How about resource pools? So, majority of our customers have a lot of tenants, and their typical resource pool setup is that, all right, for each tenant I allocate some amount of memory according to how much they are contributing to the cluster. So if you have, let's say, 10 Impala daemons, 200 GB of memory per daemon, 2 terabytes of memory, you divide into 8 tenants. This is a good design for maybe the cross spelling, but this is a very bad design from Impala perspective. Primarily because the memory allocated to a pool cannot be used by other pools. Impala runs query in seconds. In seconds, you don't have time to wait for concepts like yarn preemption. Busy tenants, where you have a lot of queries running, queries will start to queue up because it has only a limited number of memory. Small tenants running large queries will start to spill to disk because in the limited amount of memory they could not handle all of the queries that they were running, and the operator started to spill to disk. We have seen situations where customers have almost like 25 tenants or 25 pools in the Impala cluster with only few active at any given time. The recommended design for Impala resource pools looks like this. You have 3 tenants, small, medium and large. By default, give all users access to a small tenant. If a user really needs access to medium or large queries, then you selectively give them access to larger tenants. You can use other utilities like we have APIs in Cloud Manager to charge back to the right tenants according to number of queries that they have run. This allows optimal use of the entire memory that you have in the cluster for Impala, and thereby you get the ability to run more queries and everybody remains happy. Some information on metadata operations. We have seen customers running a lot of invalid metadata, and invalid metadata in today's world with HMS notification are really not required. You need to run invalid metadata only in two scenarios: when new tables are created or dropped by Hive or Spark, which actually is not required with HMS notifications today, or when the block location is changed by HDFS load balancer. Other than that, you should not require to ever run invalid metadata. You run recover partitions when new directories add in HDFS without making any SQL changes, and thereby you run a recover partition so that required partitions can be read off the disk and the HMS metadata for them updated. Lastly, a refresh table or refresh table partition. You're required to run this when data is added via Hive or Spark into the tables without using HMS notification. So let's say you do spark.write.parquet, or you do HDFS DFS put into a table directory or a partition directory. In such cases, you need to run a refresh table or a refresh table partition to get that additional files, or whether it's addition of files or removal of files, acknowledged by Impala, and Impala would refresh the metadata for those tables. An example of a scenario where customer was not aware of this and they were running like 18,000 invalid metadata on Impala per day. So to understand this, it is not required to run so many invalid metadatas with Hive Metastore notifications. You should ideally make sure that your ETL uses spark.sql or Hive commands like load table. You should run refresh table partitions, or require table partitions as and when required. Use invalid metadata only for operations like altering tables or running the HDFS rebalancer. How does the automatic metadata sync work? The catalog daemon pulls the Hive Metastore notifications, and then it informs the coordinators that okay, this table has been dropped when it sees alter table or when it sees alter table command or a add or drop partition command. It adds the tables when it receives a create table or create database event. It removes the tables from the catalog when it receives a drop table or drop database event. Operations that do not generate events in Hive Metastore, such as adding new data into existing tables or partitions, are not supported. So you still need to run a refresh table partition, especially when you do spark.write.parquet. If you're doing spark.sql, that will generate a Hive Metastore notification. Let's talk about compute stats. Compute stats is very CPU intensive. Based on number of rows, number of files, the total amount of data, and the file format, it takes a significant amount of time to generate stats. For partition tables, the stats are calculated per partition, whereas for unpartitioned table, they are for the entire table. You should always limit the stats collection to only the required columns, and the required columns are the columns that are used in the join and the group by clauses. You should recompute stats only when you change more than 20 to 30% of the data, and you should run compute stats ideally only on weekends or night times, or times when the cluster is not used that much. You don't really need to collect it after every data load. You can enable stats exploration, and that allows you to say that compute stats on the basis of just 10% of data or 20% of data, which is now GA for all customers. Where collecting stats is very time consuming or a very manual process, you can also set them manually. You can set them manually by setting num rows, by using alter table command, set table properties num rows equal to xyz. You can also set the number of rows for a specific partition using the same thing. So alter table, table partition, table name, partition name, and then you say num rows is equal to something. You can also set column stats manually. This is ideal where you have a lot of control on your ETL processes, and rather than running a compute stats in Impala, you would use your metadata from your Spark jobs, for example, to just set the statistics when you're loading data, for example, in Spark streaming jobs into Hive tables. You can use those jobs to just set these stats. Some other scalability considerations, ideally use star schemas and integer join keys. We have seen joins on integer keys to be significantly faster than character keys. You check for hotspotting, you increase the replication factor for your master data or frequently queried data. By increasing the replication factor for those tables, you make sure that queries that are joining, let's say, a customer dimension or a date time dimension or a product dimension, don't hotspot on certain executors, because that is where the replicas of that limited master data is. So you replicate your master data, say if you have a very large cluster, let's say 10 times. Thereby you get a much more smoother performance where there are a lot more replicas to choose from and you don't hotspot. You avoid casts. We have seen over 10% improvement, especially for our large telcos where they were casting strings as integers or integers as strings. You can increase the runtime filter wait time. What this does is Impala waits more than a default amount of time for statistics to be available from the earlier join steps or the earlier filter steps or the earlier scan steps, and thereby your overall performance of queries actually becomes better and faster. You can use SDFF file handle caches. Make sure that you are given enough free memory for the OS to cache data blocks. Always set the default compression codec. In today's world, you can set it to Z standard or LZ4. Use high CPU nodes, so this is more longer term. So if you are setting up a cluster just for BI use, knowing that your query concurrency is close to a number of threads that you have in executors, you would want to select machines with, let's say, 32 × 264 core machines, thereby giving you a good 128 threads on the cluster and making sure that you can run that many concurrent queries. If you are hopping data from one environment to other environment, you can distribute data from a remote cluster where you do the ETL, and after you finish your ETL, you can load data into a BI cluster just for your reporting use cases. A little bit about BI tools. We have BI tools like you, we have BI tools like others that access data. By default, they don't always close queries because they are BI tools. Hue is a web browser, and a web browser doesn't always close queries. We recommend proper settings in Hue, proper settings in other JDBC web-based applications, where you should always set idle query timeout and idle session timeout, and thereby these queries would be closed after the query and the session timeout. This allows Impala coordinators to free up resources and not continue to leave the queries running, waiting for the client to basically fetch more data. Handcrafted SQL is always recommended. This is simply because some of the SQL complexity that we have seen in Impala comes from tools that are generating overtly complicated SQL strings, and this typically happens because BI tools make a universe or make a semantic layer that is very obtuse, and when the actual query is generated from that semantic layers, it has a lot of nested tables and nested definitions and views and aliases and a lot more. In such cases, using handcrafted SQLs over pre-generated SQLs makes performance a lot more better. You can also have different pools for different workloads, where each workload runs in its own pool. So you could have pools for JDBC use cases, pools for users coming in via Hue, pools for access coming in from tools like Tableau or ClickView or Spotfire. Always make sure that end users set mem limit. So either set a default at a pool level and make sure that they run queries in their pool, or set a default in their queries. Let's talk a little bit about query profiles. Impala query profiles can be retrieved from Cloud Manager via the UI, or just by running a profile semicolon command on the Impala shell command line. It includes nanosecond timers for all operations on all of the nodes. It is quite detailed and exhaustive runs into pages, but we'll look at the aggregate information on it, which is very easy to understand and parse. So some questions that customers want to answer. What's the bottleneck in this query? Why is it running slow? It ran fast in the past, but it's running slow now. Why? How can I tune the query to improve the performance? So when you look at query profiles, you should always look for a couple of things. You should check, what Impala version you're on, what are default query options. So if you see some query options over here, the first thing that comes to mind is, hey, somebody disabled code gen. Somebody has sent empty dop to 0. By disabling code gen, Impala, rather than building a C++ code to execute queries, tries to interpret that data, which is a lot slower than a vectorized code that can be understood by a CPU and executed. Check the state of the query, whether it's running, whether it's completed, whether it's failed, what's the state. Check the type of the query, that will tell you whether it's a DDL, DML, or something else. The first thing to check is what is the peak memory usage per node. This will tell you how much amount of memory this query required on each of the nodes when it was running the query. So if you see over here, the peak memory required was 1.131 GB on the smaller node, but on the larger node it was 6.80 GB. Now what it shows over here is a huge skew in the memory required on the average node, which was around 1.3, 1.2 gigs, and on one of the nodes that was around 6.8 gigs. What this tells you is there is something on that node that is skewing up data. It could be a data skew, that there's a lot of data read on that node. It could be a join skew, that you have a lot of rows that have a value of, let's say, custom ID equal to 1, and causing all of them to go on that particular node, causing that node to require a lot more memory. It could be a aggregation skew, where post aggregating, once again, there are a lot of rows that are with some value, and all of those nodes are aggregated on all of those values, all of the rows with those values are aggregated on that particular node. So skews are important. Check if your data is skewed and what you can do about it. For completed queries, you will get summary, as you see here. This will tell you a lot of information about how many hosts were involved in the query, what's the average and max time for that operator across all of the hosts, what are the number of rows that it returned, what were the estimated number of rows when it was planning the query, what's the peak memory required, and what's the estimated peak memory that required. What you see over here is you can look for skews in data, you can look for skews in the processing time, and look at how many rows Impala estimated versus how many rows were actually returned to see whether heuristics or stats are properly collected or not. You can also look at how much memory was estimated versus how much memory was required to see whether Impala is underestimating even the memory required for a query or not. You can also check whether join orders are correct or not. You check whether partitions are correctly pruned or not, and whether the right hand side is smaller than the left hand side or not. If you look for some of the information over here, you see the join type, whether it's a hash join or a broadcast join. You'll also see whether how many partitions are scanned for a particular table. When you go down in the query profile, you understand the query compilation timeline, the query timeline, and the timeline after the query has finished, where it is waiting for the query to be closed. Here you will see some things like whether metadata is available or not. If the metadata is not available, then how much time did it take to load the metadata by requesting it from the catalog talking to the name node and the HMS, and sending that information back to the coordinator. So it tells you how much time it takes to retrieve the metadata. In this case, you see it was 9.6 seconds. It will analyze the query, it will generate a single node plan, which would then be contributed to a distributed plan, and then it will see planning has basically completed. When the query starts to run, you will see query was submitted and at what time was it admitted. If your queues are busy or you don't have enough memory, you will see that the query has started to queue, and the time required for admission will actually go up. After the query is selected from the queue to be admitted and run, you will see the query starting to run by saying all backends were started, and filters were received from the other nodes as required, and at what time were rows available. Here you see that the first rows were available in 2.7 minutes. Once first rows are available, you will see how much time did the client require to retrieve data from the coordinator. So you'll see that the last row and the first row was fetched very fast. This resulted in not too many rows, and hence the query was fast. And finally, the query was unregistered at 2.8 minutes. A lot of times when you run queries via JDBC applications or applications like you also see a client fetch wait timer being significantly large. Here you see the client fetch wait timer was hardly 1 second, but sometimes you see it to be very long. When you look at the plan of each of the queries, you also see partition pruning information. As you see as example over here, it shows that the table has 96 partitions with 2,936 files with a total size of 681 GB. You see over here how many partitions were accessed, and here in this case it was accessing all partitions. Right. What you see over here is even though stats were available, the data was not partitioned by the columns on which you are searching for, and hence you are reading all the partitions of a table. Sometimes you can prune partitions, sometimes you cannot, but irrespective of that, it is important to understand whether the statistics that you have, whether the partitioning that you have on the table is able to prune your queries or not. Here when you are reading data from 600, you are reading 681 gigs of data, it is obviously going to be a little bit slow. Some key takeaways. So our recommendation is always to use dedicated coordinators and executors. Always enable Impala admission control and set the default memory limit or the min and the max memory limit. Metadata management is significantly improved in the latest version of Impala with on-demand metadata, and follow best practices for query and performance tuning that we have documented online. The link is here for reference. That's it from me. Thank you so much for your time. If you have any questions, you can reach out to me at manish@cloudera.com. Thank you so much.